All right, picture this. You're out in the middle of the ocean on a ship, nothing but salt water for thousands of miles. So where does your drinking water come from? Well, today we're heading deep into the engine room to find out. We're going to look at this amazing machine, the Alfa Laval AQUA, and see how it pulls pure, fresh water right out of the sea.
Okay, so deep down in the engine room, with all the noise and heat, you'll find this thing right here, the freshwater generator. And yeah, it might look kind of unassuming, but don't let that fool you for a second. This machine isn't just some nice-to-have gadget, it is literally the ship's lifeline. Every single drop of water for drinking, for cooking, for cleaning, it all starts right here. I mean, without it, the crew can't survive and the ship isn't going anywhere.
But here's the really brilliant part. This machine doesn't need its own furnace or some huge power supply. Nope, it just runs on waste heat from the main engine. I'm talking about energy that would normally just get dumped into the ocean. So the big question is, how on earth does it pull off this little bit of magic?
All right, so let's get into the science of it. And, the secret isn't actually magic. It's just really, really cool physics. It all has to do with what happens to water when you stick it in a vacuum.
So we all learned in school that water boils at 100 degrees Celsius, right? But that's only true at normal atmospheric pressure, like we have right here. Now look at what happens when you create a vacuum. By sucking out most of the air, you can get water to boil at around 40 degrees Celsius. I mean, that's basically lukewarm, like a warm bath. It's incredible.
And this whole clever trick is called vacuum distillation. It's the key to making this whole thing work so efficiently. Think about it. By making the boiling point so low, that lukewarm waste heat from the engine's cooling system is suddenly hot enough to make seawater boil and turn into steam. It's an absolutely brilliant way to recycle energy that you'd otherwise just be throwing away.
So, this is where all the action happens, right inside this stack of titanium plates. You've got two things going on here. On one side, you have the hot water from the engine. That's the red part. On the other side, you have seawater. Now, the heat zips through those plates, and because of the vacuum, the seawater just flash evaporates, turning into pure vapor and leaving all the salt and gunk behind. That pure vapor then rises up and is ready to be turned back into water.
Okay, so that's the science. Pretty clever, right? But what does it actually look like to get this thing running? Let's switch gears and put ourselves in the boots of a marine engineer for a minute. We're going to walk through how they bring this machine to life.
Starting this machine up isn't just flipping a switch. It takes a methodical approach. First things first, power on. Then, you gotta seal the whole system up by closing the air bleed valve. Next up, you start the ejector pump. That's what begins pulling the vacuum. You watch that gauge like a hawk until it hits the sweet spot. Then you can start the freshwater pump, and finally, you slowly, carefully introduce that hot water from the engine to get the whole process cooking.
And this is the command center. It might look simple, but from this little panel, the engineer runs the whole show. They're watching those gauges, listening for the right hums and whirs from the machine, the sounds that tell you everything is working just right. It's a job that takes real focus and knowing this machine inside and out. And that vacuum we talked about, it's absolutely crucial. The target, the magic number you're aiming for, is between 85 and 95%. If you don't hit that, the water just won't boil the way it needs to. I mean, the entire process, everything, depends on hitting that number.
And look at this. Every single part, no matter how small, has a huge job. This little thing is the air bleed valve. Now get this, in really cold seas, the system can actually work too well. It starts making fresh water too fast and the purity can drop. So the engineer uses this little valve to let a tiny bit of air back in, just to slow things down and keep everything stable. It's all about that fine-tuned, precise control.
All right, so the machine is up and running, but the engineer's job isn't done, not by a long shot. Now their job shifts to monitoring. This is called the watch. It's all about being vigilant, making sure the machine keeps humming along and the water it's making stays perfectly pure.
And during the watch, there is one main villain, a silent killer you're always fighting, scale. As that salt water boils off, it leaves behind all its minerals, right? Calcium, magnesium, and that stuff builds up on those hot titanium plates. This scale acts like an insulator, and if you let it go, it will literally choke the life out of the machine and just crush its efficiency.
So how do you fight it? Well, one of your key weapons is maintaining the right feed-water ratio. The easiest way to think about it is like this. For every 1 part of fresh water you make, you've got to flush out over 2 parts of super concentrated salty brine to get rid of those minerals. If you get greedy and try to squeeze out more fresh water, all you're going to do is build up that killer scale even faster.
Your other main weapon is a chemical one. From this tank, a special anti-scalant is constantly being dripped into the seawater feed. But, you see that warning symbol? This isn't stuff you mess around with. It needs to be handled carefully and measured exactly right. And that is a huge responsibility for the engineer on watch.
And that chemical is a specific one called Alpacon Altreat 400. It's basically this polymer liquid that creates a slick coating on the plates so the scale can't get a grip. But check this out. You have to mix it into a solution, and that solution is only good for 1 week. So you can see the kind of planning you need at sea. Every single week, without fail, the engineer has to mix up a fresh batch of this stuff.
But look, even with all that care and all those chemicals, eventually you just have to do a full-on cleaning. And this is not a simple job. We're talking about a complete overhaul where the engineer has to roll up their sleeves and really get their hands dirty.
I mean, just look at the instructions from the manual. They're so blunt, so to the point. You're not plugging in a laptop to run diagnostics here. This is a physical, tough job. The plates get cleaned in an inhibited acid bath, and all that means is that the acid is designed to eat the scale, but not the super important titanium plates themselves.
And this is where the real hands-on work begins. The engineer has to take the heart of the machine apart. We're talking about removing these massive bolts, sliding the whole frame open, and getting to that stack of titanium plates. Each one of those plates has to be dipped in a warm acid bath, scrubbed by hand with a soft brush, checked for any little bit of damage, and then put back together just right. It's a slow, painstaking process.
And the stakes here? They are incredibly high. A single line in the manual says everything you need to know. Be careful not to damage the gasket. Think about that. One tiny slip-up, one little nick in a rubber seal, and you could lose the vacuum. And if you lose the vacuum, the ship's only source of fresh water is completely out of commission.
So that leaves us with this question. What does happen when a machine this important needs work done and you're thousands of miles from land? The answer is, the engineer has to handle it. The whole thing, from the brilliant science of it all, right down to the greasy, hands-on repairs, it all comes down to the skill of the ship's engineers. So next time you see a ship out on the water, just think about the incredible work happening down in that engine room, turning that vast, salty ocean into the very thing that keeps everyone on board alive.